Okay, this lesson also on rational functions and their characteristics is going to focus only on the horizontal and the slant asymptotes. So there was a previous video that covered other properties. So this video is only going to talk about these two. And then we also do mention the limit notation, which is mainly used like in an AP pre-calculus class when we're going over these. So let's just look at some of the properties. We already know what the definition of a rational function is from a previous video. It just looks like a fraction. So you have a polynomial in the numerator and denominator. Now looking at the leading terms of both the numerator and the denominator. Okay, so we're going to say that ax to the m is the leading term of the numerator, p of x, and bx to the n is going to be the leading term of the denominator, q of x. So your general form, which we had before, was just your polynomial is called p of x over q of x. So now we're just looking at the leading terms. So the horizontal asymptotes and the slant asymptotes really only are concerned with the end behavior. So what are essentially the tails of the function doing? Where are they going? And so that is what we're going to investigate. And so if we're doing a horizontal asymptote, we know that if you have a polynomial in general, that there's essentially four different cases to consider for end behavior where the tails could be going. But if we have a rational function, we're going to actually look at the ratio of the leading terms. So ax to the m over bx to the n, and we're going to break it down into three scenarios that will happen. So the first scenario, calling it case one, is the numerator power of this leading term, right? The m, x to the m here, the m could be less than this power, right? So if the m is less than the n, then we're going to say there is a horizontal asymptote, and the equation of it is just going to be y equals 0. Okay, y equals 0. That means that this basically is going to get really large, and the numerator is going to get really, really small, get close to 0. And so over time, the end behavior, it's going to be approaching 0. Now, their case where you have m equals n, so they have the same degree. The numerator and denominator have the same degree. You have a horizontal asymptote, and you can think of if the degree is the same, those would cancel out. And so the function is going to eventually just approach this value, y equals a over b. And so we'll say y equals a over b is the horizontal asymptote. And then finally, case three, if this power is greater than this power, so the power in the numerator is larger, this is the case where we will not have a horizontal asymptote. Okay, so there's going to be no horizontal asymptote. Now, while we're on it, the horizontal asymptotes, let's go ahead and mention the end behavior. So if B is your horizontal asymptote, then the function is going to approach that as x goes to the right or gets very large, and as x goes to the left or gets very large. Okay, so your function will approach that horizontal asymptote b. So that is your limit notation for this one. Now, going back over here, going over here to the slant asymptote, this is going to happen when in a specific case for case three. So you have the numerator degree larger than the denominator, but specifically if it's exactly one more, right? So one more than the degree of the denominator. So for example, like an x cubed up top and an x squared in the bottom, right? So it's just one more. If that's the case, then you get a slant asymptote. And the way we're going to find the slant asymptote is you can do long or synthetic division to divide the polynomials. You're going to divide the denominator into the numerator. And as soon as you get the quotient, you're pretty much done. You don't need the remainder or anything like that because the slant asymptote is going to be sitting right there in the form y equals mx plus b, right? So you're going to get a linear equation. Now, the limit notation for the slant asymptote, we know that as x is going to go out to the right or to the left, right? X goes to positive infinity, it's going out to the right, negative infinity going out to the left. The notation for the slant asymptote, the limit, it's either going to go up or down infinitely, right? So it's going to approach positive or negative infinity as x gets large and small. So let's go down here to some practice. Here's a few problems that we can go over. We are going to identify the horizontal or slant asymptote. And so we're going to use that technique that we just mentioned. So you want to look at your rational function. This is the numerator, the denominator. You may want to put it each numerator and denominator in standard form if it's not, because ultimately all we care about are the leading terms. Okay, so the leading term is going to be the term with the highest power. So we have a 3x squared in the numerator and then an x squared in the denominator. And that is all you need to look at for this particular concept. So we can see that we're in the case 2, right? If we go up above case 2, that's where the powers are the same. So you can think of it like this, that y is going to be 3x squared over x squared, but those cancel, right? So it's just going to be equal to 3. Or we could just apply the rule directly and you have the 1 here. So it's just going to be the ratio of this one over that one, the coefficients, 3 over 1, but it's still just 3. So here you have a horizontal asymptote at y equals 3. Okay. Now, number 2. Once again, we are just looking for the horizontal or slant asymptote. This is going to be a case where you have a slant. So we are looking at this term and this term, and this is the higher power. So the numerator has a larger degree. So that's a case 3, but we said it's a specific case 3 because the power here is 1 more than the power there. So that's a slant asymptote, which means we want to do some long division to find that. So let's go ahead and set that up. You're going to do x squared plus 1 on the outside. And then you have 2x cubed minus x plus 4 on the inside. Now, you may remember when doing long division, you want to make sure that you have placeholders for the missing powers. Like this one is missing an x term, and this polynomial is missing an x squared term. So let's rewrite our division problem. And we're going to make it look like this: x squared plus 0x plus 1. And that way it has placeholders. And then 2x cubed, we're going to put a 0, x squared minus x plus 4. Okay, so you want to add the placeholders. And that's all that we're doing there. Now you continue. We always start with the highest power over here divides into the highest power over here. And so x squared will divide 2x cubed 2x times. So I like to line my terms up so that the x's are lined up. So I always write it on the end, but 2x is going to go on top, and then we multiply that times each of these terms. So that's going to give us a 2x cubed. 2x times 0x, we'll just call that 0x squared. Keep your x squared terms lined up, and then 2x times 1 is going to be plus 2x. And we subtract that from all of the above. So these, I noticed that I accidentally wrote a squared there. So let me fix that. So now those should always cancel out. And we have 0 minus 0. Well, if you wish, those go as well. So minus x minus 2x, we're going to say minus 3x. And then we can bring down the positive 4. Now, we can't divide this into this. So remember, the answer is just going to be the 2x. But if you need to be reminded of that, you can think of the quotient. We normally write it like this, and then you add what's left over, which is the remainder, and then you can divide that by the divisor. Okay, so we can see this is really going to go to 0 eventually because this power is bigger. So this is really like 2x plus 0. So you can think of it like that, that's going to go to 0. So it's just 2x plus 0. So really this y equals mx plus b form, the b is really just 0. So this one, like we said, has just the slant asymptote because it cannot have both of those, horizontal and slant. So we're just going to say it's a slant asymptote at y equals 2x. And that will be your answer for this one. Now let's look at example 3. So for example 3, we're going to once again compare our degrees. And this one is the same as that one, right? You have a power of 2 in both the numerator and denominator. So if we look at those, they're going to cancel, right? The x squared over x squared if we look only at the ratio of the leading terms. And so we can see this is going to approach 5 over 7. So automatically we know we have a horizontal asymptote at, not sure where that came from, horizontal asymptote at y equals 5 over 7. And so that will be your horizontal asymptote there. So you just need to practice doing those rules. Make sure you understand when you're going to have the horizontal asymptote, when you're going to have a slant asymptote, and there could be a case where you have neither as well. So we will continue putting everything else together, like all of the graphing with the x and y intercepts and bringing in the concepts from the other video, like the holes and the vertical asymptotes, so that you can understand all of that. So keep practicing. See you in the next video.